Okay. So one of the things that we all have to deal with is information overload. We just get overloaded with information. It's very easy to get information. When I was a graduate student, we would have to go to Hamilton Library, go to what's called the Biological Archives or something like that, look up a bunch of stuff that had been published, and then from that, go to another format to find out where in the library those journals were. Then we'd have to run through the library trying to find those journals. And then you would have to find a copy machine and pay like 5 cents a page for copying it. Now, I forget whether I think it's the NIH thing, National Institute of Health. I have 2 areas of research that I was involved with. And whenever a new publication comes out, I get an immediate email with the link to it on my phone. It's crazy. I haven't been in the Hamilton Library for, I don't know, maybe a year. So now you don't have to do that. Everything just comes to you. And so here's the issue. Your generation thinks that they can just go look up anything they need whenever they need it. And therefore, why should I learn that when I can just look it up whenever I need it? But there's a problem with that because there's certain things that you need to know. And it's not just, oh, I just need to know how to look things up. No, you need to know more than that. You need to know what to look up. That's the problem that we're seeing right now. So most of the information you get, and if you think about it, look on your cell phone, look on your social media, how many ads, how many messages do you get a day? It's just crazy. And they're all trying to get you to buy something or believe in something or whatever. So that's the thing about science. It's not trivial. And it's much more important than any of that trivial stuff. But information is just so easy to get. So here's some cartoons that show that, like in 1965, yeah. So I remember as a kid, we lived on the Big Island in Kamuela, and most places had phones, landlines. But if you wanted to call your auntie, you pick up the phone, and there's other people talking. It was a party line. Everybody had to share the one line. And anyway, I just put this one in here. This is verging on inappropriateness, but I just loved it, so too bad. So in the 50s, only about 1 out of 5 homes actually had telephones. They had to share the telephone lines called party lines. And then here's a picture of Hanauma Bay, our beloved, sacred, natural preserve. In order to go down there now, you have to watch a video. You have to say you're not going to feed the fish anything different. Oh, it's just crazy. In 1956, Hawaiian dredging blasted this big hole in the reef right here because that's where they brought in the Trans-Pacific telephone cables. So when they brought that in and connected up, that allowed 48 simultaneous calls between here and the mainland. The military had charge of about 1/3 of them. And before that, most people used shortwave radios to make long distance calls. So anyway, that was a great improvement for at least Oahu. Then in 1964, they brought in a second cable from Makaha. Of course, the Makaha one, that was coming through mostly sand, so you don't see remnants of it. But if you go down Hanauma Bay, you'll see this thing that I remember seeing in high school. And I had no idea what it was, but I know it didn't look natural. That's what it was. They blew up Hanauma Bay. So another thing is this. Maybe you guys are called millennials or something. There's a kid that surfs with us sometimes, John. John's close to 40, but we keep calling him a millennial. He doesn't really like it. But why are some people lazy? And this is written by a psychologist, and it might help you understand how you were raised. And here's another thing that was written by a very frustrated woman. But anyway, you guys get a bad rap for just being in that generation, but all the generations have gotten bad raps from the previous generations. So I wouldn't let it bother you. And if your generation is considered lazy, here's what I would say. What if most of your generation is lazy and you're not? Thank you very much for all that competition going away. So most of what you see on social media, advertising and special interest groups, is bullshit. Science is designed to get around the bullshit. So what you're looking at, most people in your guys' generation, they don't seem to vote. They don't seem to be politically active. They may be politically active on an issue by issue by issue thing, but don't know anything else about anything. You guys are living in the matrix. The media and the news and all this kind of stuff basically controls everything, including what's in your darn refrigerator. Nothing based on science. I'm in, what's the word for it? The graduate faculty for human nutrition. Many of my friends are very good, well-known nutritionists, including the two that write in the newspaper all the time. And we talk about this all the time. All the supplements and stuff like that is absolute bullshit. And where I learn about a lot of it is from my son. So my son's into all this MMA stuff and everything, all of his friends, and he has friends that have supplement companies and gyms and all this kind of stuff. And one of the things that we've been wanting to do is go look at what they're actually buying, what they're using, and tell them whether it's bullshit or not. They seem to be receptive to it. But anyway, that's what I mean. So financially, here's what's going on financially. You go back to the 1950s, you see how these lines are together right here? That's productivity of our country, similar to what you would call the gross national product, the blue line. So the blue line keeps going up like this, right? Now, what happened at about 1970? About 1970, the wage earners, the people who got paid by the hour, all of a sudden their share of the productivity just started dropping off. You're supposed to be up here. So what is happening to the middle class? This is what's happening to the middle class. So where is all this money going? I wouldn't even say the 10%, I'd say the 0.1%. The richest of the rich are the ones that are getting all this profit. You're working, but you're falling behind, as is the whole middle class, and the 0.1% is getting more and more their share of productivity of the nation. This is the kind of data where you can analyze what's going on and use science, even though it's economics, that is a science, to find out what's happening. So here's the cumulative growth in income. Here's the top 1%, keeps going up just like this. And what's happening since about 1970, 1980 is the middle class and everybody else is just dropping out. What are the results of that? Here's spending on health. Here's life expectancy. So here's several other countries. Look what's happening in the United States. Okay. So our health system is suffering because of this. They did a calculation last year in Honolulu. The minimum wage necessary to buy a 2-bedroom apartment is $39 an hour. Anybody here make that?
Mm-mm.
So, got another question for you. Go back to this. If this is you, and this is the 0.1%, hopefully you're thinking, well, this is not fair. This is not right. So who allows this to happen? It's America. So one person, one vote. How does the 0.1% get its way with the economy instead of the 99.9%? One person, one vote. You can say it's corruption or whatever, but I doubt it. It's because you guys aren't voting. That's why. You guys are living in the matrix. You're just letting the 0.1% do whatever they want to your economy, to your future, to your kids' future. So I included an article at the bottom. It's called A Rigged Economy. It's written by a Nobel Prize winner in economics. I put the whole thing down here. He's an older guy. He's got nothing to gain. His career is over. He already won the Nobel Prize. But this is what he's concerned about. This is where I got this data from. So I think you should read that and learn how to wake up. So just to give you an idea, supplements are not regulated like pharmaceuticals. The federal laws prevent the FDA from testing unless it's requested by some group with medical and legal concerns. So in other words, the government allows companies to advertise supplements as if they were good for your health, even there's no evidence in humans. Even the recall is voluntary from these companies. These companies can do whatever the hell they want. And many of you are going out and spending money on all these supplements. What I'll tell you is this. People who take large amounts of supplements and vitamins and all that kind of stuff are putting them at risk for liver and kidney damage. If you don't believe me, go look it up, learn some physiology. Everything that you should be doing to your body should be doing in moderation. Most of these supplements are very high in one thing, almost nil in another thing. And even multiple vitamins. You shouldn't be taking a multiple vitamin every day. If you're concerned about it, take half of one every other day or something like that. You have to do things in moderation. Otherwise, your body has to get rid of these chemicals. It has to process all these chemicals. It puts wear and tear on your liver and kidneys. It could be doing much more harm than good. In 2015, a study estimated that tainted supplements caused 23,000 emergency room visits, 2,000 hospitalizations a year. 2013, the Drug-Induced Liver Injury Network, which is a bunch of MDs, estimated that 20% of drug-induced liver injuries were related to supplements. So the government's not protecting you. Okay. So anyway, I would suggest that you read this just so you can wake up to all of this. So any questions so far? Anybody want to buy some supplements? Okay, so now we're going to start the first part of the real chemistry stuff. And I got to say, this is really all remedial stuff. And so why do I spend so much time on remedial stuff? It's because after years of experience, I understand why people have problems with chemistry. It's not the chemistry. They have problems with the prerequisites. They have problems with the math. So anyway, I'm going to go through and show you a system of doing problems which can be applied to almost every single problem that you will encounter in this class and any other chemistry class. So just a little bit of background. Science needs only 7 fundamental units to describe everything known. And here's what they are: mass, length, time, electricity, temperature, and light. That's about it. So we've been trying to find the best definitions of these fundamental units. I went into a little bit about that. And then the metric system. This is for whatever reason gives students the hardest time. So the United States, Burma, and Liberia are the only countries that do not use officially the metric system. The metric system is meant to be a universal system. And here's what I experienced in what year? I think it was 1975. I went to the mainland. I bought a Volkswagen van. I drove all over the mainland. I wanted to see where all those tourists come from. I learned a lot. Besides that, my only other time out of the state was in the Army, where I didn't really see that much of stuff. But anyway, I remember going up into Canada, and I get into Canada and it's like, wow, the gas is so expensive over here. And I went back down into the United States, it was cheap again. And when I came back, I started taking a chemistry class, and you know what I found out? That Canada was using the imperial gallon. The United States was using the US gallon. The imperial gallon is 20% bigger than the US gallon, but they're both a gallon. You see how stupid that is? But if every country is using the liter, then it's not a problem. That's the idea with the metric system. So I put a lot of stuff in red boxes because it supports some of the learning. I don't want to put these things specifically on an exam. So here's something that's kind of interesting. And I talked a lot about this with my French colleague, who's now back in France. So the metric system was developed in France in the 1790s. And the French actually helped the United States defeat the British so we could form our country. The US Constitution was written in 1787, and then the French Revolution was a few years later. So the French helped us get rid of the British, but then at the same time, they gave them the idea of the French Revolution. And what's even more interesting is that Thomas Jefferson served as the US minister to France from 1785 to 1790, right through the French Revolution. And it was Thomas Jefferson who came to US Congress in 1789 and said, yeah, we need to use this metric system. It's going to make everything easier. So we've been trying to use the metric system since really 1789. So almost 100 years later, in 1875, the United States committed to the development of the internationally recognized metric system. We were one of the original 17 signatory nations to the Treaty of the Meter, where everybody was going to use the metric system. And guess what? We're still not using it. That's a problem. So now, calculator and math skills. So what we really need to do right now on our calculators is know how to use scientific notation. So here's a number. This number right here is not in scientific notation. Notice that it's the decimal place that tells us how big or how small this number is. If I go this way with the decimal place, the number gets bigger. So we put it in scientific notation, we take that decimal place and we move it to right behind the first non-zero integer. So we get 2.340. So now, how do we tell whether this number is big or small? Well, we use powers of 10. Every single time you move a decimal place, that's a power of 10. So let's look at where we get this 10 to the minus 5. We had to move the decimal place 1, 2, 3, 4, 5 times, right? That's where I get the 5. And why is it a negative number? It's a negative number because the whole number is less than 1. I know some of you memorize things like this. Oh, well, if you move it to the right, then it becomes a negative number. If you, yeah, no, it's just, as long as it's less than 1, it's a negative exponent. So here's how to do this in different calculators. So many of you will have a TI-30. Some of you might have a Casio, or at least this logic over here. Some of you might have a Canon. I don't know. What you're going to have to be able to do is go to your calculator and make sure that you can take a regular number, put it into scientific notation, and take a number in scientific notation and put it into a regular number. You need to be able to do that. Otherwise, people get confused. They're off by a million because for some reason the exponent doesn't show up, or they don't know how to do it, or something like that. And everybody's calculator is going to be different. So you have to do this on your own. If you do have problems with your calculator, maybe, you know, come early to the Zoom meeting or stay after the Zoom meeting and we can go through it, you know, using Zoom. But I want you to make sure that your calculator becomes a tool for you to help you to solve problems, not an issue that you don't want to deal with. Don't avoid learning your calculator. Your calculator is a tool. So here's a review of scientific notation and the reason why we need to do it. I'm going to introduce you to the mole concept. We'll do this again later. But 1 mole is 6.022 times 10 to the 23rd things. In chemistry, those things could be atoms. They could be molecules, right? They could be protons, for example. Could you have a mole of mice? Yes, you could. But the mole concept is simply the same as the dozen concept. You guys know the dozen concept, so therefore you know the mole concept. If I got a dozen chicken eggs, it weighs a certain amount. If I got a dozen ostrich eggs, it weighs a different amount. So if I have a mole of hydrogen atoms, that weighs different than a mole of gold atoms. But just like if you got a dozen, there's 12 things. If you got a mole, there's 6.022 times 10 to the 23rd things. That's it. That's it. But that's important because I'm going to stop screen sharing for a second here, because it correlates to the periodic table. So if I have 1 mole of hydrogen atoms, it weighs about 1.00794 grams. If I have a mole of, say, gold atoms, it weighs 196 point something grams.
Your blue binder.
Anyway, so that's why it's important. Okay, now where's my screen sharing again? Okay. So now let's analyze this number. This right here tells me what the number is. This part right here tells me how big or how small that number is. And this part right here tells me what those things are. So now if I were to write this out in regular notation, look how big that number is. That's huge. 1,000 is 10 to the 3. 1,000,000 is 10 to the 6th. 1,000,000,000 is 10 to the 9th. 1,000,000,000,000 is 10 to the 12th. Are we anywhere near that number?
Nope.
No, we're not. This number is huge. And we'll talk about that later. So here's some useful manipulations. So 10 to the 0 means 1 times 10 to the 0, but 10 to the 0 is simply 1. So 1 times 1 is equal to 1. 10 raised to the power of 1 is simply 10. 10 raised to the power of 2 is basically 100. If you have negative exponents, 10 to the negative 1 is equal to the inverse of that, 1 over 10 to the 1, which is 0.1. See how that works? And here's some simple manipulations. When you're multiplying, you add exponents. Okay? When you're dividing, you subtract exponents. Okay? So anyway, you should also be able to do those on your calculator. When you're punching things into your calculator, you're less likely to make a mistake than by just visually inspecting it and saying, oh, it's 10 to the minus 3 or something. So here's a little bit more about that. Just trying to summarize everything, giving you some examples. And let's see. And here's some worked problems with answers. Okay. And here's some multiplication. So this is what you're really doing with exponential numbers or scientific notation numbers when you're multiplying. You're going A times B, and then the exponents for multiplication, you're adding them. When you're dividing, okay, you're dividing A by B, but then you're subtracting exponents. And there's no reason why you couldn't do this problem right here on your calculator. If you're good with your calculator, if it's actually a tool for you, instead of something you're trying to avoid, this should be no problem.
Do you recommend a particular calculator?
Just a scientific one, like a cheap one. I wouldn't pay more than 20 bucks for one.
Okay, thank you.
And Texas Instruments seems to be one of the major ones that are in that price range.
Professor, I had a question going back to the mole.
Yeah.
So it's written here, 1 mole equals 6.022 times 10 to the 23rd of something.
Right.
And that's always the case, whether it's atoms or protons, mice, or anything.
Right.
Is this formula for 1 mole the same thing as Avogadro's number?
That is Avogadro's number. Yep.
Okay, thank you.
Yep. Well, thank you. Thanks to Avogadro. Okay. I'm screen sharing, but it doesn't look like I am. Are you guys seeing where it says addition and subtraction?
Yes.
Yes.
Okay. Because usually it's outlined, but now it's not outlined for some reason. Okay, so here's some addition and subtraction with scientific notation. Notice that when you do stuff like this, you have to have the decimal place lined up. So here the decimal place is lined up because that includes the exponent. So in other words, you can't take a number like this and a number like this and then get 4. Okay? You have to have the same power of 10, otherwise the decimal points are not lined up. And then again, if you do the whole thing on your calculator, you won't get the answer wrong. So here's some powers of exponential numbers. So here's something cubed, right? To tell you the truth, because I'm so used to picking up a calculator that's handy, I have calculators all over the place, they're all different. I simply told myself a long time ago, I'm not going to memorize how to use every calculator with exponential numbers, you're using your y to the x function and all this kind of stuff. It's just too much work. So if I have to do something simple like this, you know what I would do? In my calculator, I would put 3 times 10 to the 4th times 3 times 10 to the 4th times 3 times 10 to the 4th. Then I get my answer, and I don't have to worry about what calculator I'm using. So here's kind of an overall summary of that kind of things, what you should take away from that review. And again, I do hope that you take that review as a way to also get good with your calculator. So questions at all so far?
Questions?
Okay. So now we need to understand what is the direct proportion. So the equation for a straight line is y is equal to mx plus b. So here's x, here's y. So what we're saying is that these straight lines right here are described by this mathematical equation right here. M is the slope of the line. So here we have a line, a series of lines that have different slopes, different values for m. B is the intercept. So look what happens. What do we mean by the intercept? If I set x equal to 0, mx is now 0, and then y is equal to b. So when x is equal to 0, what is y? That's the value of b right there. So these 4 lines right here have the same value for b and different values for m. Then I did another one where they all have the same slope, but they have different values for b. See how that works? Now, of all those lines that you see, only one of them is a direct proportion. That's the blue one. And I think what I did throughout this whole chapter is that everything that's a direct proportion I put as a blue when I was graphing it. So what's the deal about a direct proportion? At at x is equal to 0, y is equal to 0. What? The only way that can happen would be if b is equal to 0. Okay. So if b is equal to 0, in other words, if it passes through the origin, that equation now becomes y is equal to mx. So what determines x from y is simply the m, which is the slope. And it turns out that the slope is a conversion factor. If I have x and I need to convert that into y, I simply read up here and come over this way, and there's the answer right there. that make sense? So direct proportions give us conversion factors. So get down to some real basic stuff. Here's a meter stick. At the beginning, that's 0 centimeters. At the end, that's 100 centimeters. But that's also equal to 1 meter, which is also equal to 39 inches. So look what conversion factors we have here. 1 stick is equal to 1 meter. What if I got 2 sticks? Then that should be 2 meters. What if I got 0 sticks? Well, that better be 0 meters. But I can do the same thing. Ignore the stick and say, well, 1 meter is also equal to 100 centimeters. 100 centimeters is equal to 39 inches. 1 stick is equal to 39 inches. 1 meter is equal to 39 inches. These are all equalities. And what if I were to graph sticks versus meters? It would be a straight line passing through the origin. It's a direct proportion. So what I'm going to do is simply take this simple conversion right here, which you know this one. You've been doing this since you were, I don't know what, 2nd grade or something. So 1 meter is equal to 100 centimeters. Okay, that's an equality. Now what if I take this and I mathematically divide both sides by 1 meter? So I would get 1 meter divided by 1 meter, 100 centimeters divided by 1 meter, right? No mathematical violation there. But then, what is 1 meter divided by 1 meter? That really turns out to be 1, isn't it? So now this relationship right here is equal to 1. And guess what? In math, you can multiply by 1. You can divide by 1. The inverse of 1 is 1. 1 is a magic number. So what I'm going to do is generate some data. 1 meter is 100 centimeters. 2 meters should be 200. 0 meters should be 0 centimeters, right? And I graphed it. And what do I get? A straight line passing through the origin. B is 0. So the equation for that is y equals mx. So now we're going to calculate the slope of this line. The slope of a straight line is the change in y divided by the change in x. The change in y divided by the change in x, right? So on this case, I took 300 centimeters and 3 meters as one data point. Then I took 100 centimeters and 1 meter as the second data point. So here's the change in y. Here's the change in x. And look what it turns out to be. Oh, wait a minute. The slope of our line is the conversion factor, which is m. You get that?
Professor, when you say the origin, is that always 0?
Yes, right. Yep. So think about it. Say I needed to convert 2 meters into centimeters. I would go up here, read over there, there's my answer. What did that conversion for me? The slope of this line. So what I'm trying to say is that for a direct proportion, the slope of the line is the conversion factors. So there's several ways to convert between meters and centimeters. 1, you could use this graph. 2, you could use a meter stick that has centimeter markings on it. 3, you could use the equation y equals mx. But what if M or X, excuse me, what if X was like something like 5,000 meters? If I'm going to use this graph, oh my God, I'm going to have a huge graph. If I'm going to use a stick, I got to have a huge stick. So the best alternative would simply be using y equals mx. Here's m right there.
Quick question,
Yeah,
just to make sure. So if m is the slope and m is the conversion factor, and y equals mx, y is the conversion, like the answer?
no, y is this here, whatever is here, and x is whatever is here.
Okay.
So if
Thank
I
you.
had y is equal to 200 and I wanted to know what x was, I would come over here and simply read down there.
Okay.
And what got me there was the slope of this line. If the slope of this line was different, then I would get a different value, right? So the slope of the line determines the correlation between this and this. That is your conversion factor.
Okay.
So get that also be the conversion factor for if it was an indirect proportion? Would M still represent a conversion factor?
No. The conversion factor is only when it's so simple that b is equal to 0, and then y is simply equal to mx. Okay. So when I was talking about it up here, these, in order to solve a problem over here, you have to use the entire equation, y equals mx plus b. Same over here, because b is not 0. So the only time you can do this is when b is equal to 0, and then it is a direct proportion. It's the only time.
Okay, so B has to be equal to 0 in order for the formula to be a direct proportion.
Yes. Yep. So now, understanding that, which may take a while because I know it's not taught that way, but if you understand that, let's figure out how it's going to help us solve problems. So here's a typical problem. Convert 2.66 meters into centimeters when I gave you the conversion factor. So I'm looking at this problem right here. This I know is a conversion factor. It has more than one unit. This right here has only one unit, so you can't convert it with anything. So that's what you're starting with. So I simply write down that number with the unit. Then I realize that this is a direct proportion. What I need to find is the slope of the line, the conversion factor. So I'll leave a space for the conversion factor. Then I'm looking at the problem. Well, I'm starting out with meters. Where do I need to end up? Oh, centimeters. So now I have this part set up. And once I have this that I'm starting with and this that I end up at, I can then determine what has to go in here. Whatever goes in here, I have to be able to cancel out meters and have centimeters left over. Now that I have the units in here, I can actually see where the numbers go. Going back to the conversion factor, what number is associated with meters? A 1. The centimeters? A 100. Does that make sense? And the last thing I do is simply I do the math. And what we did mathematically, because this is the slope, right? That's m. We simply took x multiplied by the slope, and we got y. Okay. But do I need to think about this? No, I just need to have this method down. That's how we're going to solve problems. So believe me, I did not learn this way as a kid. I learned how to solve everything by ratio proportion methods and memorizing just like everybody else. But when I figured out this method, it's like, well, wait a minute, this is the best method for direct proportions. How do I know this answer is right? Well, I have everything written out for me in a nice sequence. Did I write the problem down correctly? Yes, I did. Do meters cancel out and centimeters stay left over? Yes. Is this the truth in here? Is 1 meter equal to 100 centimeters? The answer is yes. Did I do the math correctly on my calculator? Yes. I absolutely know that this is the correct answer because I followed this procedure. The biggest problem students have is they might even know the conversion factor, 100 centimeters in a meter, but then they write down 2.66 and now, oh, do I multiply or do I divide by this? 50-50 chance, right? Well, looking at the units solves that problem. You will get it right every time. So these type of simple conversions, according to this website, is taught in 4th grade. So yes, it's remedial, but I do say I'm teaching it in a way you've never seen it before. So now here's some graphical representations. This is a straight line passing through the origin, meaning that that is a direct proportion. And the reason why this is important is because this is really a chemical reaction. If I got so many grams of explosive, I get that big of a bang. If I double that, then I'll get that big of a bang. If I don't have any explosive, then I should get 0 bang. That just tells us that chemical reactions are direct proportions. So what about real life? What about money versus happiness? It's a direct proportion, right? Okay, well, I don't know about that because I don't have data up here. I have data only down here. It makes me wonder why all those millionaire Hollywood stars are so unhappy all the time. But if they were to donate some of their money to me, then I could collect data up here and then I could find out whether it's a direct proportion or not. So here's some that are not direct proportions. It's a straight line, but it certainly isn't a direct proportion. So the desire to improve the world does what to your income? The more idealistic you are, the less likely you are to make a lot of money. I first started thinking about this a long time ago when I took on a foster kid. He was the same age as one of my own kids, a neighborhood kid. And his family had problems with drugs and somebody died and all that kind of stuff. So he was kind of a troubled kid. And it's like every time there was trouble, a social worker would be involved. And every time there was a different social worker. Like, what happened to so-and-so? Oh, he left. What happened to so-and-so? Oh, took a different job. And I realized, I looked it up, it's the social workers in the state of Hawaii, like any other state, are some of the lowest paid government employees. Why is that? Because society is taking advantage of them. Oh, you want to improve the world? Okay, if you really want to do that, you really want this job, let us pay you less. They make less than garbage people. Here we are, the state of Hawaii, 100% Democrat. We're all about the people. Okay, what people are you talking about? And here's another one that is not a direct proportion. This is called an exponential increase. This would be an exponential decrease. Okay, so you have squared and cubed and stuff like that inside the equation. So what I found also that the number of fame, it doesn't matter whether it's good or bad, the more fame you get, the more money you make. You folks ever figure out who the Kardashians are? If you go look that up, you will be quite disgusted. But they are millionaires, if not billionaires. So here's a problem. I'm hoping to advance your understanding of what a direct proportion is. So two workers, Mary and Harry, are both paid $400 for a 40-hour work week. Now you could probably figure out that that turns out to be $10 an hour. So what is the slope of the line? $10 per hour. But Harry is such a good worker that he's given a weekly bonus of $25. So give the equation for each of these two workers. It's either y equals mx or y equals mx plus b. So Mary is simply y is equal to mx. $10 per hour at the number of hours gives you the income. Same thing for Harry, except in addition, he gets that bonus of $25 a week. So Mary's income looks just like this. It's a direct proportion. Harry's is everything is the same except for what? B is equal to $25. It's not equal to 0. So this is not a direct proportion. So how much money would each make in 1 week after working 45 hours? So Mary would simply get $450. I simply use y equals mx. But Harry, I got to use y is equal to mx plus b. I have to use the entire equation in order to get the answer, because it's not a simple direct proportion. Hopefully that makes sense. So what do you need to memorize for the first exam? I put them all here, and you're familiar with many of these, and you don't know that you're familiar with many of these. So here's the base unit. We don't give any Greek symbol to it. So for example, 1 meter is simply equal to 1 meter, or 1 gram is equal to 1 gram. But what the heck does kilo stand for? Kilo, in other words, small k, means 10 to the minus 3. So 1 kilometer means 1 times 10 to the 3 meters. 1 kilogram is 1 times 10 to the 3 grams. So that, I'm sure you know. Mega, I'm hoping that you know. What is a megabuck? It's $1 million, right? Then what's 1,000 times bigger than a mega? A giga. Giga is a billion of something, and tera is a trillion of something. So would you rather have a gigabuck or a megabuck?
I'll take the tera.
Well put, you'll take it. So then if we go the other way, we have the deci, which is 1/10 of something, right? So 1 decimeter is 1 times 10 to the minus 1 meter. So all we're really doing is taking the D and replacing it for what it stands for. We just have to memorize what these letters stand for. So centi is 1/100th of something. By the way, this really points out that our money system is really the metric system, isn't it? A dollar, and what's a centi dollar? A cent, right? So milli is 1,000th of something, micro is a 1,000,000th of something, nano is a 1,000,000th of something. You've heard of nanotechnology, right? You're talking about making like little tiny machines out of individual groups of molecules and stuff. And a pico is a 1,000,000th of something. So many of these are in common usage, like computers, for example. So information is in terms of bits. So 1 bit we don't normally talk about, but what is a kilobyte? Kilobyte is 1,000 pieces of information. So that's on the order of files, right? Like a small Microsoft Word file. Megabyte would be on the order of maybe some computer programs and some large files, like the files that I produce that we're looking at right now. They're very large because of all the graphics and everything. And gigabyte and terabytes and all this kind of stuff is used in storage media. And, you know, there's people that will tell you how many gigabytes their iPhone has, but they don't know what a gigameter is. No clue. It's the same. It's just simply using the metric system. So, no offense to women or anything, but the computing power of the early computing devices were measured in kilogirls. It had to do with how fast or how much information that an office girl could put into a computer, like per hour or something like that. So in 1965, it was changed to floating point operations per second, or flops. So modern supercomputers are petaflops, teraflops, things like that. And to give you just some idea of relevance to biological things, plant cells are somewhere between 10 and 100 micrometers, okay, which is that many nanometers. Animal cells are often a little bit smaller. Bacteria are another quite a bit smaller. And viruses are even much smaller. Here's the nuclear pore. So anything that goes in and out of your nucleus has to be smaller than this. Here's the size of a ribosome. The ribosome is the protein that produces other proteins. And here's the typical globular protein. So now we start going into nanometers or maybe even into picometers. Here's DNA. It's actually the width of DNA. I didn't put that for some reason. Here's the diameter of a hydrogen atom. Here's the diameter of a hydrogen nucleus. So in the lab here, I could show you all kinds of filters that I have around here. Normally, when we're doing cell culture, we're trying to keep bacteria out, okay? So we take our media and we filter it through 0.2 micron filters. So here's the 0.2 micron filter right here. It will take out most bacteria. All plant and animal cells will not be able to go through that filter. What about viruses? Will a virus be able to go through that filter and contaminate your cell culture? The answer is yes. Will a virus go through your COVID-19 mask? The answer is yes. But the virus particle is not simply by itself. It's in a droplet of mucus or water or something like that, which would be physically filtered because the drop is going to be bigger than 0.2 microns. It's also going to be chemically filtered because when that moist droplet hits the mass is going to absorb it, and that virus particle would be adhered to your mask. Does that make sense to you?
Professor, will we be tested on these size comparisons of biological structures?
No, like in the beginning, I was saying that anything in a red box is not going to be on the exam. Yeah.
Okay.
Mm-hmm. But I think I put it there because it really increases your understanding, which is really what the goal is. Of course, some people don't like that. It's like, oh, I only want to know what I want to know for the test. Yeah. Anyway. So here's some very simple ways to do things. So how many meters are in 25 picometers? All we have to do is take the P and replace it for what it stands for. That's all you have to do is memorize what the letters stand for. Now this is not proper scientific notation because the decimal place is here. So I had to move the decimal place over 1, right? And while we're at it, maybe here's a good way to think about that. This number cannot change, right? So when I move the decimal place from here to here, that's like I divided by 10. So to keep this number the same, I had to take this part of the number and multiply by 10. So 10 to the minus 12 times 10 to the 1 gives you 10 to the minus 11. Okay. Or like I said, you just put it into your calculator. Your calculator will do that. So here's another example. Okay. Then you should also know one conversion factor between the US customary system and the metric system. And I don't even want to, I'm going to call it the US customary system. I'm not going to call it the British system because the British officially use the metric system. Maybe not everybody in Britain, but they do. So you should know one for mass. So I always remember that 1 kilogram is 2.2 pounds. And I call that the drug dealer's conversion factor. Any drug dealers among you? Okay, well, I kind of expected no answer on that one. Just think about it. If you're a drug dealer, you got to go to some foreign country and you're going to buy a kilogram of something because they use the metric system. Then you need an airplane, you need a submarine, you need, I don't know, a package of balloons, whatever you got to do to get it back into the country without getting busted. And then you got to convert it into the US customary system. If you do it wrong, you might get killed because it's a nasty trade. The other one that you might know is that 1 pound is about 454 grams. So if you know one of these, then you will never be lost about converting between our system and the rest of the world. Then for length, I always remember this one because I was a little bit confused as an undergraduate. We had to memorize everything when I was an undergraduate. So 1 inch is exactly 2.54 centimeters. Now that definition was not exact until 1959 when they redefined the inch to make that an exact conversion. And in 1959, they were thinking, well, we're not going to be using the inch for much longer anyway, so let's just change it so this is at least one thing that's easy to convert. Then for volume, you should know that a liter is about a quart. Okay. So now which one is bigger? If I had a quart bottle and I poured a liter into it, then 0.057 of that would spill over. So the liter is actually slightly bigger than a quart. Okay. So anyway. So the metric system is superior in so many ways. Matter of fact, if you look at the US customary system, is there any relationship between, say, a pound and a foot? Absolutely none. Any relationship between a foot and a yard? Well, yeah, but it just basically makes no sense. But here's within the metric system. Here's a cube where each side is 1 centimeter. So the area of this cube is 1 centimeter times 1 centimeter, which is 1 cubic centimeter. The volume would be 1 cubic centimeter cubed, which is equal to 1 cubic centimeter, 1 cc, which is also equal to a milliliter. See the difference there? Now, if you look on hospital equipment like syringes, oftentimes on syringes, they'll show you the marks in cc's, but a cc is the same as a milliliter. So how many milliliters in a liter? It's 1,000, right? Because you memorize what M stood for. M is 1/1000th. 1/1000th of a liter. That's what that says right there. So a liter is made up of 1,000 of these. So we have a whole bunch of other things that are in semi-common usage, especially when you go to physics and stuff, you start combining units like the Newton, for example, which is a measure of force, is kilograms times meters per square second. But right now, we don't have to worry about any of that. So altogether, you have 14 conversions that you should know. 10 within the metric system, 3 that go between the different systems, and then you should know that 1 cubic centimeter is equal to a milliliter. That gives you 14. Okay. So in your resources folder, there should be a file. I forget what it's, oh, here's what it's called, conversion study card. So the way I designed that, if you were to print that out double-sided, then cut it up along the lines right there, you'll have flashcards to help you memorize for the exam. Hopefully, your printer works right. So let's look again how to write conversion factors. 1 centimeter is equal to how many meters? All we're doing is replacing the C with what it stands for, right? Now, what if we were going the opposite direction? 1 meter is equal to so many centimeters. Okay, how do I do that? This C stands for 10 to the minus 2. So what I have to do is put a 10 to the plus 2 here. Well, why? Because 10 to the plus 2 times 10 to the minus 2 gives you 10 to the 0, which is equal to 1. So what I'm saying is that, I don't think I can do it. Nope, it won't let me do it, but this part right here is equal to 1. So what's in front of the M? A 1. What's in front of the M over here? A 1. That's why these are equal. So how does it read? 1 meter is equal to 100 1/100ths of a meter. And that's the truth. Okay. What about up here? This means that 1/100th of a meter is equal to 1/100th of a meter. That's true. So here's another one, similar type of thing. And then what you need to do is check to make sure that what conversion factor you write down is correct. So here's something that you're very used to. 1 cent equals to $100. Is that correct? No. There's 100 cents is equal to $1. That makes sense. What about this? That doesn't make sense. That makes sense. But what we're really doing is we're reading what we wrote and we're carefully making sure that we have it right. For some reason, I see so many careless errors, it's sad. So what about this? Is this right or wrong? 100 meters is equal to 1/100th of a meter. No, that's not correct. How do I fix it? I just change the sign of the exponent. Now it reads 1/100th of a meter is equal to 1/100th of a meter. So let's just do a problem here. We have one-step conversions, we have multiple step conversions. So I'm going to show you a bunch of different things, all using the same methodology that makes it unlikely that you're going to make a mistake. So here's the problem: convert so many centimeters into meters, given the conversion factor. So this has 2 units, that's the conversion factor. This has only 1 unit, so I write it down. Then I realize it's a direct proportion, so I need to get the m, I need to get the conversion factor to put in here. I want to convert centimeters into meters. And now that tells me exactly what has to go in here. I have to be able to cancel out meters, cancel out centimeters, and keep meters. So I set the problem up using the units. Now I have to put numbers in here. So if I'm using this, 1 is associated with centimeters, 10 to the minus 2 is associated with meters. So I put that in there, do the math, and here's the answer. Okay. So would I do this on my calculator? Maybe, maybe not. This one is easy because you can do it in your head, right? You're simply adding exponents. What about 2-step conversions? Convert so many centimeters into micrometers. So what I'm saying is that you do not have a conversion factor to go directly from centimeters to micrometers. You did not memorize it. So we'll break it up into 2 steps. Each step you do know. So what's between centimeters and micrometers? The base unit is simply meters. So we'll go to meters. So I converted centimeters into meters. And then I have meters and my intermediate answer, and I have to go to micrometers. That means I have to get rid of micrometers. I have to get rid of meters and keep micrometers. And is this the truth? 1/1,000,000th of a meter is equal to 1/1,000,000th of a meter. Yes, that's the truth. Okay. So here you're subtracting exponents. So -6 minus the -6 could give you 0, right? Into the 0. So at this point, sometimes I get students to tell me, well, that's long. That takes a long time. It's like, no, it really doesn't. But here is a fast way to do it. Same methodology. You multiply by 1 twice. So first I know I have to get rid of centimeters and go to meters, right? So I put my conversion factor here. Now, if I would have done that math, I would have meters, but I got to get rid of meters and keep micrometers. That way I'll get micrometers in my answer. So let's see if we set it up correct. Start off with centimeters, end up with micrometers. Did I write the problem down correctly? Yes, I did. Do centimeters cancel out? Yes. Do meters cancel out? Yes. Micrometers will be my answer. Now, are my conversion factors correct? 1/100th of a meter is equal to 100th of a meter. Yes, this is correct. That's equal to 1. What about this one? 1/1,000,000th of a meter is equal to 1/1,000,000th of a meter. That's also correct. Did I do the math correctly? Yes, I know I have this answer correct. This way is extremely fast and it's extremely accurate because you can come along and see and check all your work to make sure that you're correct. So here's a question. What if I would have made a mistake in this one? What if I would have put 1 micrometer is 10 to the plus 6 meters? My question is, would you have caught it? That's my question. And I'm saying if you write it out like this or like this, the likelihood of you catching that mistake is pretty good. If you don't use the units to set it up, you're going to have mistakes. Okay. So any questions on that?
I have a question.
Yeah.
Like looking at the syllabus, you would want us to like finish and go through like this entire document by like today?
No, there's no real deadline. The only deadline is when exam 1 is, when it ends, and when I put deadlines for the homework.
Okay.
Yeah. So, I mean, you know, some people, this is all review. Some people are like, oh, wow, I didn't do this for a million years. But this is a remedial chapter. It really is. So right now, everybody's going to be working at their own pace. Some people will be challenged by this, and they'll need extra help. Somehow we got to give them that extra help. So please email me if you need the extra help. And some people are like, yeah, this is so simple.
Okay. All right, cool.
So here's some advice. Don't combine conversion factors. That's my advice. It's too easy to make mistakes, but I'm going to show you how to do it. Okay? So look, here's what we know. If I had to do that same problem, I know that 1 meter is equal to a million millionths of a meter. I also know that 1 meter is equal to 100 100ths of a meter. Because this is equal to a meter, and because this is equal to a meter, therefore they're equal to each other, right? So now, since this is an equality, it can be used as a conversion factor, because it's all the direct proportion. So then I can put the units in there directly, and I got the right answer. But now here's the problem. The process of going through here, if you don't write it out step by step, how are you going to check this? This is much more difficult to check, in my opinion. And you want to know that your answer is correct. So I think this is the much easier way, because instead of trying to check 2 conversion factors that are combined, you're simply checking them without having to combine them. I think it's faster and more efficient. And then this is a joke. So my wife was at Farrington High School teaching chemistry and physics for 13 or so years, and I was their robotics coach. And this kid, Jeremy, who's from the housing, and he showed me this joke. Oh, how to convert between kilometers and meters, right? You just cancel out the K. We never realized how smart Jeremy was, but he graduated from UH with a degree in math and a degree in electrical engineering in 3 years. EE is generally a 5-year degree. It takes people 5 years to do all the prerequisites and everything. So then Jeremy's like, oh, I'm not going to take a job until I get, I think it was $80,000 a year. And we're like, yeah, right. Sure enough, he got a job. Took him 6 months or so after graduating, but he got a job with, I forget what company it was, a big high-tech company for more than $80,000 a year. And because he was like a kid, they brought him over, picked him up at the airport, and gave him his own condo. I don't even think he had a driver's license at the time. Anyway, yep. From the housing. So here's some examples. So worked out examples, painstakingly worked out examples. If you've ever had to do something like this in Microsoft Word, you know. How to convert micrometers into inches. So I'm looking at this problem right here, and it's like, you know what? I don't know how to get from micrometers into inches. But what do I need? But what do I know how to do with micrometers? I know how to get micrometers into meters. So I'm just going to do that. I can't be wrong because all I'm going to do is multiply by 1. So now I'm at meters and I'm thinking, do I know how to get from meters into inches? Well, if I know that conversion factor, yes, I can just use it now. But if I didn't know this conversion factor, I knew the one about centimeters. Well, then I'd go from meters into centimeters and then go from centimeters into inches. But here's my point with this. All we're doing is multiplying by 1, later on multiplying by 1. That's all we're doing here, it's multiplying by 1. So now here's the problem. You have to go tell your family members and everything else that what did you do in college today? Oh, we multiplied by 1. But you're not going to make a mistake if you're simply multiplying by 1. So you can start the problem, work it a little bit, see what you got, and look around and figure out where do I go to the next point. You don't have to have a plan to go directly from the beginning to the final answer. I love it because it's like how I drive. Say I'm going to leave work, so I look around for my car keys. That's what I'm focused on. Then I go down the elevator. Then I go to the parking lot. They have to find my car. Then I get into my car. Then I turn the car on. Then I'm like, well, which way is out of the parking lot? I don't plan every step along the way to get home because I'm confident that all the individual steps are going to be done correct. And that's what's so helpful with this method. So here's some conversions between area and volume. Area is 2-dimensional. So convert 55.5 square centimeters into square inches. Oh, wait a minute. That's squared, not just centimeters. Well, look, write down the conversion factor, and then that's an equality. So just like if you have this kind of a conversion factor, if you square both sides, there's nothing illegal about that. So 2.54 times 2.54 gives me 6.45 something. Centimeters times centimeters is square centimeters. And same with inches, right? So now we have the conversion factor between square centimeters and square inches. Now I can do the problem. So I have, this is my original problem. I need to get rid of square centimeters, keep square inches. So what number is associated with the square centimeters? 6.45, and with the square inches, a 1. Now I just simply do the math and there's the answer. What about volume? So liters into cc's, cubic centimeters, and then into cubic inches. Oh, okay. Well, first of all, I know to go from liters into milliliters, right? 1 liter is 1,000 1,000ths of a liter. So now I got milliliters. I also remember one of my 14 is that 1 cubic centimeter is equal to a milliliter. Now I have the number of cubic centimeters. So I need to cancel out cubic centimeters and keep cubic inches. So how do I get that conversion factor? Same methodology. Here's in the one-dimensional respect, that's an equality. So if I cube both sides, I get 2.54 times 2.54 times 2.54 gives me 16 something cubic centimeters is equal to 1 cubic inch. Then I can do my conversion into cubic inches. So what we just did is the basis of almost the entire course, because chemistry is almost entirely the direct proportion. So when we come back the next time, we'll do something that is not a direct proportion, and that is the temperature scales. Okay. But we'll stop here. But this whole part of the chapter here is about what is the direct proportion, why is it important, and how to do problems that use the direct proportion. And using your calculator. Okay. So, let's see, where are we? Man, there's a lot of stuff in there. So next time we'll do temperature scales and talk about some other stuff. Here's some practice, right? Some review. So we're almost done with this. So what we just went through is the major skill for this course. You get this down, you'll have no problem with the course. So any questions so far?
Will there be any quizzes or homeworks before tomorrow's class?
Yeah, I think I'm going to put some up today. Now for tomorrow, I have a problem. At noon, I have a system meeting that I have to attend. So I can't do a Zoom at 1. I mean, at noon. I could do it after 1 or just not do it. We'll just pick it up again on Friday.
Sorry, I wasn't here yesterday. Is there a daily Zoom call?
Well, not necessarily. For the biochem course, we're going to have to do something every day. For the Chem 100 course, maybe it's every other day.
Okay.
So now I'm thinking, do I do a Zoom after my meeting tomorrow? I know the people that could make it are kind of, there's less people can make it after 1 o'clock. So I'll tell you what I'll do for tomorrow is I'll do a Zoom either at 1 o'clock or 2 o'clock. I'll look at who can make it most often, but I'll make it a lot of review stuff, and I won't just like be powering through a bunch of stuff that people need to catch up with. Okay. And this afternoon I will put, I'll start putting up the homework and the quizzes. Okay. But you do have the hard copies of them to get started on it. Okay. So any other questions?
Will you put these on the announcements?
But what on the announcement? When is the Zoom?
Yeah, like the Zoom and like,
Yeah, sure. Because I'm not going to like search the internet and find when the Zoom's going to be. That's
Okay.
ridiculous. Yeah, I'll let you know. Yeah,
All right.
I'll look at the poll that I had before to find out when people can make it. Yeah.
Okay.
I'll let you guys know. Okay, well, you guys have a great day. Take care now.
Appreciate you.
Thanks, you too.
Take care. See you.